Hopefully you guys can see me, hear me, and see my slides. Is that true, all of it? Awesome, thank you. Okay, we have a lot to get through today because I'd like to finish chapter 4, and so there's not going to be any brain teasers because we're going to jump right into using our brains for chemistry. First, just putting up the same exact announcements that I had up last week. A reminder for you guys that you have an Achieve homework due this Wednesday morning, and the chapter 4 quiz will be in class on Wednesday. There will be 1 or 2 questions from the parts of chapter 3 that didn't make it onto exam 1, just to make sure that nobody leaves behind their cyclohexane chair forms. Here are all sorts of resources for you guys, including SI sessions that are tonight at 6 p.m. that might be helpful for you. In terms of having the format of our our quiz on Wednesday, I would like for everyone to come to class, come to the Zoom room at 1 o'clock on Wednesday like normal. We will have the quiz during class, but it will not take the whole part of class. So I'd like to meet together at 1 o'clock on Wednesday here in the Zoom room like usual. I'll give you guys a short, brief, contained lecture and then release you to take the quiz on Canvas. But please, please, please come and be on time because you won't know when to start the quiz otherwise. Okay. So, like I said, I'd like to get through the rest of chapter 4 today. We got a good start on it last week. We got all the way through introducing free radical chain reactions by looking closely at the chlorination of methane. Then we talked a lot about thermodynamics, and we finished up by relating Gibbs free energy, delta G, with KEQ. I gave you an equation for that, and we also talked about it a little bit more qualitatively. Today, what I'd like to do is finish up thermodynamics by connecting delta G to some other thermodynamics terms, delta S and delta H, and we'll see that over the next couple of slides. And then we'll talk about kinetics. Then we'll apply it to the reaction types that we were talking about last week, and we'll kind of close out the chapter with some loose ends. Someone has put in the chat box about the quiz. It will be during class on Wednesday, but I need everyone to show up here in the Zoom room at 1 o'clock. We'll do a little bit of a lecture and then I will tell you when you can go start the quiz. So it's important that everybody comes here. And then that way also, if there's any information that I have to give you before the quiz, you'll have it. Okay.
Sorry, will the lecture be on chapter 4?
Depends on how far we get today.
Okay, thanks.
We might move on to chapter 5 if I can get through everything today, but the quiz material will not go past what we cover today. All right, so the quiz will be chapter 4 and a little bit of chapter 3. And if I don't finish chapter 4 today, I will not quiz you on anything that I haven't gotten to today. Hopefully that makes sense. It's the natural, reasonable way to do things. But I'm hoping to get to all of it. So let's go ahead and get started. Like I said, we're going to finish up thermodynamics. And so let's pick up where we left off. This equation here shown at the bottom of your screen is the second thermodynamic equation that I'm asking that you guys know. Again, let me say this out loud. You guys need to know this equation. So this equation takes our same Gibbs free energy, the same delta G that we were talking about last week. And instead of connecting it with KEQ, we can now connect it with a couple of different other thermodynamic features. One of them is called enthalpy, delta H. This you may have heard too as the heat of the reaction. So this delta H refers to heat generated or energy generated or consumed in the reaction. And delta S for entropy. Entropy is a sense of disorder or a capturing of a measurement of the disorder of a system. And that entropy term is temperature dependent, right? So the temperature plays into the delta G of a reaction by impacting how the entropy works out. So let's drill down into each of these. Actually, before I do, I should mention that enthalpy, the delta H for a reaction, we can calculate this using bond dissociation energies. And we'll see some examples of how to do that in the slides coming up. So first I want to start with entropy because it is something that we are actually not going to spend a lot of time or energy on. So I kind of want to tackle it, get it out of the way, and put it to the side. What entropy is talking about, the measurement of entropy, measures how much randomness or disorder or freedom of movement there is in the system, and it measures, so a delta S measures the change. And yes, I can go back to the equation. Delta G equals delta H minus T delta S. Okay, so in the next slide, we'll be talking about this T delta S term and specifically the delta S term. And again, I'll post these slides after class. Okay, so for entropy, again, delta S describes the change in a randomness or disorder of a system. Are there 2 particles turning into 3 particles? That's an increase in randomness and disorder. Are there 3 particles that come together to make 2 particles? That's a decrease in randomness or disorder. So entropy is connected with heat and volume. All of these things are connected with the capability of a system to be chaotic or disordered or random. And the last bullet here refers to spontaneous reactions. So remember, spontaneous reactions are ones with a negative delta G. Those spontaneous reactions favor systems that increase disorder. They favor systems that increase disorder and minimize enthalpy or the heat needed to do things. And this should make sense to you, right? Like if you never do your dishes, the spontaneous thing that'll happen is that you will have more and more disorder in your kitchen, right? If you never clean your room, the spontaneous thing that will happen is more and more disorder. You have to put in work to generate order. And so that putting in of work means that a reaction is not spontaneous. Okay, like I said, though, entropy is something that we will not deal with all that much as organic chemists. This is going to be something that is kind of minor, and it's important that you guys know about it in terms of the equation, that it does and it can play a role in the overall impact on delta G. So let me go back for a second. So it does factor into delta G, but usually in most of the organic chemistry reactions we're going to see, this delta S term is very small. And so the T delta S term is very small. And what happens then is that whatever your delta H is, if it's strongly negative or strongly positive, that's going to be the major influence on delta G. So the T delta S term is overall pretty minor. And so this is literally all that we're going to do or say about it. And that's it. We're done with entropy. And that's what that last bullet says. Okay, so entropy done. Small, but important to know about because it is a factor in delta G. Enthalpy, however, is going to be the major factor, and that's going to be something that we do need to think about. And again, delta H is called enthalpy formally, but it's also can be thought of as the heat released or absorbed during a chemical reaction. And it can be calculated. And if it's negative, that change in heat, if it's a negative delta H, that means that heat is being released. That gives you an exothermic reaction. If the change in delta H is positive, that means you have to absorb heat to get the reaction to go. And that means that reaction is endothermic. So reactions are going to favor exothermic reactions because that's going to be the lowest enthalpy of the system overall, or will give you the strongest bonds. That's another way to look at it or think about it. So enthalpy is nice for chemists because we can calculate it. Delta H can be, like I said a couple slides ago, can be calculated from bond dissociation energies. And so we'll see that over the next couple of slides. One thing I want to point out here is that these words, exothermic and endothermic, go with H, delta H. And an easy way to remember this is this TH here for exothermic and endothermic looks like the TH in enthalpy. And if you review our slides from last week, there are some similar words, endergonic and exergonic, that go with delta G. So delta G, which is a G, goes with the exergonic and endergonic, which refers to the overall energy of the system that accounts for both heat and disorder. So both delta H and delta S are contained within delta G, which means when we're talking about endergonic or exergonic with that G term, We're talking about the overall free energy of the system. Okay, so like I said, delta H we can calculate using bond dissociation energies. So in order to do that, we need to take a moment and really make sure we understand what bond dissociation energies are. If we want to break a bond, typically that requires energy. Typically we have to put energy in because that bond is a bond because it's given the molecule some extra stability. So in order to disrupt that bond, we have to put in a little bit of energy. And so a breaking of a bond is a positive bond dissociation energy. Likewise, when we form a bond, we get some stability associated with forming that bond. And so bond formation releases energy or has a negative bond dissociation energy. And given these two things, the bond dissociation energy for a particular bond, and then knowing whether we're making it or breaking it, we can use those things to estimate delta H for a reaction. So the bond dissociation energy, by definition, has to do with the homolytic cleavage of bonds. What I mean by homolytic cleavage is that when you break that bond, one electron goes to each side. So each atom involved in that bond gets one electron. So if we look here at the breaking of the sigma bond between the two chlorine atoms in molecular chlorine to give us two chlorine radical atoms, that bond has a delta H of 242 kilojoules per mole. Because we're breaking the bond in this reaction, it's listed as a positive number here. But that's the energy associated with this bond. Other ways of looking at bond cleavage are heterolytically. So in heterolytic cleavage, both of the electrons of the bond go with one of the atoms, usually the most electronegative atom. So this is going to be, I'm going to take a moment and make a distinction here that sometimes can be confusing. So I want everybody to listen up for a second. We can use bond dissociation energies, which are based on homolytic cleavage values, to calculate the delta H for any reaction, for any and all reactions. It doesn't matter if the reaction actually proceeds with a homolytic cleavage or a heterolytic cleavage. Usually in organic chemistry, it's actually going to be a heterolytic cleavage. But what we're doing here is using the bond dissociation energies because what we're really asking about is the distance in the bond stability at the start point and the end point. And it doesn't matter what the path is we took to get there. We just want to know the difference between the start point and the end point. And that's why we can apply bond dissociation energies, which are about homolytic cleavage, to any and all reactions, whether they're about homolytic cleavage or about heterolytic cleavage. Okay, so let's see it in action. First of all, how do we know what the bond dissociation energies are? Well, somebody figured it out experimentally. Somebody did the experiment, calculated these numbers, rather than not calculated, but like measured. They measured these numbers. And here is a chart that has a whole bunch of them. So in order to calculate the delta H from a reaction, we actually have to know these numbers. That means that when, not if, but when I ask you guys to calculate the delta H for a reaction, I will provide you with a chart that includes the numbers that you need. It might include additional numbers, so you have to pay attention for which numbers it is that you need. So here is our calculation for delta H for our model reaction, the chlorination of methane. So the overall reaction is shown here up at the top. And again, as a reminder, in our chlorination of methane, we are going to be breaking a carbon-hydrogen bond and breaking a chlorine-chlorine bond. And then we're going to make a carbon-chlorine bond and a hydrogen-chlorine bond. And again, I'm not talking about how this happens at all. We know how it happens because we talked about that last week. But how it happens doesn't matter. What we're asking about here for delta H is only where did we start and where did we finish? So we can use our chart like on the last slide, and we can find the energy associated with the chlorine-chlorine bond that we're going to break is plus 240 kilojoules. And the energy associated with the carbon-hydrogen bond of methane is 439 kilojoules per mole. So these are per mole. We add those up and get a total number of kilojoules per mole or kcals per mole, either one is fine, of energy that we have to put in to break all the bonds that we need to break. We do the same thing for the bonds that we're forming, except of course it's going to be negative because we're getting some energy back because we're overall approaching more stable system. So we're going to find our HCl bond on the chart, get that number, find our CCl bond on the chart, get that number, and add those two together. Now to get the delta H for the overall reaction, we just add these things together, right? We add the positive bond dissociation energy of our bonds being broken, and we add that to our negative bond dissociation energy of our bonds being formed. And we get negative 103 kilojoules per mole overall delta H for this reaction, or negative 25 kcals per mole. Again, it doesn't matter which units you use as long as you use the same units throughout the calculation. Okay, what does that mean? We just calculated the delta H for our reaction, and it's negative. What does that mean? It means it's exothermic. Cool. So we just figured out that if we want to do this chlorination of methane, we can expect that it's going to generate some heat. It's going to be exothermic. And also, because I've told you guys that usually delta H equals delta H minus T delta S mostly has to depend on the delta H term, we can also make a pretty good guess that our chlorination of methane will have a negative delta G also, which it does, which we actually talked about it in the slides last week. I told you what the delta G was for the chlorination of methane. And someone has asked, so are the products always going to be negative in the equation? So it is not necessarily that the products are going to be negative. It's that the bonds formed are going to be negative, right? The negative sign here refers to bonds that are being formed. Bonds that are being broken will have a positive sign. So typically, yeah, you're breaking bonds from the starting materials and making them in the products. So typically, it correlates with starting materials and products, but I don't want you to think of it that way because that gets away from the actual fundamental principle underneath it, that the positive delta H has to do with bonds you're breaking because you have to put energy in to break those bonds. And then negative delta H has to do with bonds being formed because you get energy back when you form those bonds. Okay, so that actually covers us for thermodynamics. We've just solved everything that we need to know for right now about thermodynamics. So I just want to take a moment and recap for you guys. Last week, we talked about delta G as it relates to KEQ, or the equilibrium constant. So we talked about how this free energy, delta H, has to do with the overall energy of the products and reactants of the system, and that a negative delta G tells you that that reaction is favorable or spontaneous. We connected it mathematically to the equilibrium constant for a reaction, and this should make sense intuitively and mathematically that if you have a large KEQ, the products are favored and your delta G will be negative. Whereas if you have a small KEQ, your starting materials will be favored and delta G will be positive. Today, what we did is took our same delta G here, and we connected it, instead of with an equilibrium constant, we connected it with enthalpy and entropy, which are other thermodynamic values. And we talked about how entropy is a very small factor, and so we can typically kind of ignore it, but we have to remember it exists. And we talked about how delta H is something that we can calculate from bond dissociation energies. That means that we can actually take a chart with some information and use that chart to figure out delta H and then make a leap of faith that that delta H will tell us something about delta G and whether or not that reaction is spontaneous. Okay, so now that we've gotten our thermodynamics out of the way, we got to get into kinetics. So the next section that I want to talk to you guys about is kinetics and the activation energy. So when I'm talking about kinetics, what I'm talking about is rates of reaction, right? Before we were talking about thermodynamics, which means what are the different levels of things at equilibrium. But you can have something that has an equilibrium that really favors the product, but it takes years and years and years to actually do that conversion, right? And so that would not be a reaction you would want to do for your pharmaceutical manufacturing plant. You would want to look for a reaction that goes faster than that. So kinetics is also equally important to thermodynamics in trying to understand chemical reactions and to be able to use them for our, purposes, either good or evil. So in kinetics, we're going to figure out the rates of equations and we can actually, the rates of reactions, and we can actually write an equation to describe that. So this is going to be a mathematical equation that describes the rate of a reaction. And generically, if we have this reaction where A and B are coming together to produce products C and D, we can write a rate law or a rate equation, these are interchangeable terms, that says that the rate of the reaction, the overall rate of the reaction, will be the constant, some constant, that's a rate constant that is specific to this reaction. You'll see later that it's also specific to a particular temperature. But we have a rate constant, and then it may be dependent on one starting material's concentration to some power times the other starting material's concentration to some power. So the exponential powers here, the little a and little b, are going to be called the order of the reaction for that particular species. I'll show you guys some examples over the next couple of slides that I think will help drive this home. Right now, it's a little bit too generic to make connections, probably. But the other thing that I want to say about these rate laws is that they are not predictable. We can't really look at a reaction on paper and know what a rate law is going to be. As you get more and more experience of a chemist, you can make a pretty good guess at what it might be based on other similar things you've seen, but you can't just look at it and know. So these rate laws that I'm talking about here have to be determined experimentally. And the way we do this is by holding everything in the reaction constant except changing the concentration of one component and looking at what that does to the rate. So let's see some examples. Here again is the generic version and all of the definitions for the generic version. And we're going to look at this reaction where we have a bromomethane or methyl bromide, either one, you guys don't need to know the name, but this methyl bromide reacts with hydroxide anion and basically replaces the bromide with that OH group. So that's the overall reaction here, is that this bromide gets replaced with an OH group. So now, experimentally, if we want to know the rate law for this reaction, what we do is we run the reaction under whatever conditions we feel like and measure the rate. And then we run it again, where this time we double the concentration of methyl bromide, but don't change anything else. And we look at what happens. And it turns out when we do that, the rate of the reaction also doubles. Okay, so we know that the rate of the reaction depends on methyl bromide. Then we do the same thing where we go back to our original conditions and then double only the concentration of the hydroxide ion. When we do that, when we double the concentration of the hydroxide ion only, the rate of the reaction also doubles. So we know that the rate is proportional, in this case, linearly proportional, to each of the starting materials. And so what we can do is we can write a rate law that looks like this. The rate is equal to always some constant times the concentration of one reactant times the concentration of the other reactant. Both of these exponents here are the number 1 because it's a 1-to-1 ratio. If you double the concentration of HBr, you double the rate. If you were to quadruple the concentration of methyl bromide, you would quadruple the rate. It's a direct linear relationship there. So what we can say, the words that we can use to describe this reaction now, is that based on this rate law, which we have just experimentally determined, that the reaction is first order in methyl bromide and first order in hydroxide. So it's first order for each reagent. And it is second order overall because we can add up all of the exponents to give us the overall order of the reaction. Okay, I see a question in the box, but I'm going to ask you to hold off until the next slide because it'll answer your question. So this case, we have methyl bromide combining with a hydroxide ion to do this reaction, and we have a second order overall rate. Now we're going to see another example. So instead of methyl bromide, we have tert-butyl bromide, but otherwise this reaction looks very similar, right? We have a bromide that's being replaced by a hydroxide. So let's do the reaction and do our rate law, experimentally determine our rate law again. And so in this case, here's what we see. When we double the concentration of the tert-butyl bromide, we double the rate of the reaction. So that's the same as what we saw with methyl bromide. So the reaction depends on this tert-butyl bromide. When we double the concentration of the hydroxide ion, though, in this case, it doesn't change the rate of the reaction. We can mess around all that we want with the concentration of this hydroxide ion, and it doesn't change the rate of the reaction. So in this case, for this reaction, the rate is proportional only to the tert-butyl bromide. And so this is the new rate law. And so in this case, for this reaction, based on this set of experimental results, our rate is that we have a rate constant times the concentration of only tert-butyl bromide. So what does that mean for the order of the reaction? Well, it's first order in tert-butyl bromide. It's also first order overall. And we can also say that it is 0th order in the hydroxide ion, because the hydroxide ion, if we wanted to write it in the rate equation, we could write the hydroxide ion with a 0 exponent, which would be 1, mathematically 1. And so it would kind of go away. That term goes away. Okay, so let's look at these one more time in comparison to each other. So here's the first reaction that we saw, where our rate is dependent on both of the substrates, and it's a second order overall reaction. Here's the second one, where our rate is dependent only on the tert-butyl bromide, and so it's a first order overall reaction. So I want everybody to take a minute and think for yourself, what does this mean? So when we're talking about the rate of reaction, we are talking about what is happening in the rate determining step, which molecules and also how many of them are involved in the rate determining step. So what that means is that for this first reaction, in the rate determining step, one molecule of the methyl bromide and one molecule of the hydroxide need to come together and meet each other somewhere. In this second one, we don't need the hydroxide at all. All we need is one molecule of the tert-butyl bromide to initiate a reaction. That's the rate determining step. So another thing to point out about these rate laws is that the rate law or the rate equation, those terms are interchangeable. They depend on the mechanism of the reaction. So even though these reactions look very similar to each other, we're just replacing a bromine with an OH group, we can tell from these rate laws that they proceed through dramatically different pathways, right? In one case, the hydroxide ion participates in the rate determining step, and in the other case, it doesn't participate at all in the rate determining step. Of course, it participates in the overall reaction because it's involved in making a new bond, but it's not participating in the rate determining step. Okay. The next thing that we need to talk about related to kinetics is called the Arrhenius equation, which is going to also show us, let us into what the activation energy is. So this equation that I'm showing you guys on the screen now is called the Arrhenius equation. It's another equation that you need to be familiar with. And I'm not going to say you need to have it memorized, but you do need to be familiar with it and understand what it means. So I've got our generic rate law up in the corner. And what this equation tells us is that the rate constant, the Kr, little kr, the rate constant for a reaction is dependent on the conditions of the reaction and very, very, very importantly, specifically temperature. So in this mathematical equation, you can see that the rate constant is dependent on a couple of constants, right? A and R, which are constants. Also depends on temperature, though. And finally, it depends on the activation energy of a reaction. So what's the activation energy? Well, the activation energy is defined as the minimum kinetic energy that is needed to create a reaction, to let a reaction occur. Excuse me. So the activation energy is best, I think, described on a reaction coordinate diagram. That's the easiest way to see it. So here is a generic reaction coordinate diagram. We start out with some reactants A and B. We go to some products C and D. Just to point out, this is an exothermic reaction because the products have a lower energy set of bond heats than the reactants, right? So starting with our reactants, remember last week we talked about the top of the mountain is transition state, where bonds are partially formed or partially broken, whereas the valleys or the low points on the curves are intermediates or discrete products where they have fully formed or fully broken bonds. So the activation energy, or E sub A, is shown here, and it is the amount of energy that we need to reach that transition state. So it's the energy you have to put in to climb the hill to be able to go down the hill on the other side, right? So this rate constant depends not only on the temperature, but on this activation energy and the size of that activation energy. Okay, so where do we go from here? Where can we take this and what can we do with it? Well, this just defines transition state and activation energy, which is what I just said. What we can do with this is think about then, what is the impact of raising the temperature of a reaction? So let's think about that. So this graph looks a little complicated at first, but I'm going to walk you through it and we'll see where it's going. First, focus on this black trace here. This black trace is at room temperature, the distribution of energy, internal energy, kinetic energy, if you will, that molecules have. So if you have a beaker of molecules at some temperature, they all have some intrinsic energy to them, right? They've got bond vibrations happening. They're kind of bumping around in solution. They're not all identical though, right? The same way that normal average human body temperature is 98.7 or 98.6. You guys, there's 150 of you guys. I don't know how many are here today, but there's 150 of you guys. You don't all have a 98.6 degree temperature, right? If we put you all together and average your temperature, it should be around 98.6. But there's going to be a distribution. Some of you might be a little warmer, some of you might be a little colder, and there's a distribution in energy. The same way with a bunch of molecules. There's, out of a population of molecules, there's going to be some molecules that have a little bit more energy, some molecules that have a little bit less energy. So at room temperature, this is the distribution. That's what the distribution looks like. So if we have a reaction that has, for example, an activation energy of 4 kilojoules per mole, then only this little fraction of molecules would have enough energy to get that reaction to go. And if we have a bigger barrier, if we have a higher activation energy, like 40 kilojoules per mole, that fraction gets even smaller. And the bigger we get with our activation energy, even smaller. So up here at 80 kilojoules per mole, pretty much none of our molecules are going to react at room temperature. If, however, we raise the temperature of our beaker, we're going to shift this population distribution to be just a little bit more higher in energy. And what that means is that now at this lowest energy barrier, if that's the reaction that we want to do, if it has an activation energy of 4 kilojoules per mole, all of these molecules now have enough energy to do that reaction. Even at the highest activation energy barrier, we still have a little portion that can go on to do that reaction. So what this means is that the higher the temperature, the more likely it is that you're going to be able to get enough molecules with enough energy to do that reaction. Okay, does this mean we should just raise the temperature on all of our reactions? What do you guys think? No. So this rule, this Arrhenius law and the rate constant being dependent on temperature, that's true for all of the reactions, right? It's true for all reactions, the reactions that we want to happen and also the reactions that we don't want to happen. So it is not a good solution to just heat the snot out of your reaction because you probably will get a lot more of other stuff in addition to maybe some more of your product. Okay. So the last thing that I want to talk about with respect to kinetics and activation energy is that we need to go ahead and think about what happens in multi-step reactions, because in fact, the radical chain reactions that we talked about as our model system for this chapter, it's a multi-step reaction, right? There's 2 propagation steps that occur to go from the methane to chloromethane. So when we have a multi-step reaction, we can find what the slowest step is by finding the step with the highest activation energy. And when we find that step, it turns out that that will be the rate limiting step for the overall sequence of reactions. So it doesn't matter if it's 2 steps or 15 steps, whichever one has the highest activation energy is going to be the slowest step, and it's going to determine the whole rate for the whole system. So here is a reaction coordinate diagram for the very reaction we've been talking about as our model system. These are the two propagation steps in the chlorination of methane. In the first step, when that chlorine radical that came from that initiation step, when that chlorine radical abstracts a hydrogen atom from methane to give you the methyl radical and chlorine gas, that has an activation energy of 17 kilojoules per mole. You'll notice that the intermediates here, the methyl radical and chlorine gas, are a little bit higher in energy than the starting material. So this is actually a little bit endothermic or endergonic, depending on which kind of a chart this is, probably both. The second step of the reaction, though, is highly exothermic or highly exergonic. It has a small activation energy, only 4 kilojoules per mole. We know the units because they're over here. And then the products have a lot more stability associated with them. So here in our first step, we have a higher activation energy. And that means that this very first step is the rate limiting step of the reaction. So the rate limiting step in this reaction is that very first hydrogen atom abstraction. And it is because this activation energy is large relative to all of the other activation energies of the whole multi-step reaction. Okay, so what we would like to do now is take all of these things that we've been talking about, take the thermodynamics concepts we've been talking about and the kinetics and activation energy concepts that we've been talking about, and let's see what it means for us in real life. Okay, so we've been talking about the chlorination of methane, but what I want to do now is expand on our radical halogenation, our chain reaction, and make our situation a little bit more complicated and see how these thermodynamic and kinetic principles really will help us understand more about what's going on. So instead of doing our radical chain reaction as in the chlorination of methane, what happens if we want to do the same type of reaction, but we want to chlorinate propane instead of methane? So now keep in mind, when you look at methane, all 4 of those hydrogen atoms are identical, right? They're all the same. So it doesn't matter which hydrogen atom that chlorine radical abstracts, you're going to get the same product. If you look at propane, though, 6 of the hydrogens, the ones on the end of the molecule, are the same as each other, and the 2 in the middle are different. So when that chlorine radical abstracts a hydrogen atom, it now has a choice. If it abstracts one of the 6 hydrogen atoms on the end, the product will eventually be 1 chloropropane with the chlorine at the 1 position. If it abstracts one of the 2 hydrogens in the middle, you'll get 2 chloropropane. Now, look at this for just a second. I just told you there are 6 hydrogens that could lead to this product and only 2 hydrogens that could lead to this product. Yet the product that's favored is the one that is statistically unlikely, right? If all things were equivalent, this product would not be favored, but it is favored experimentally. So that means they're not all equivalent, right? Statistics aren't what's dictating this. Chemistry is dictating this. Thermodynamics is dictating this. So let's see what that looks like. Before I get to that, what I need to do is define some terms for you guys. When you have a carbon that is attached to only one thing that's not a hydrogen, that's called a primary carbon. And so all of the hydrogens attached to it are called primary hydrogens. If you have a carbon attached to 2 things that are not hydrogen, that's a secondary carbon. And so the hydrogens attached to it are secondary hydrogens. Over here on the far right, if you have a carbon that's attached to 3 things that are not hydrogen, that's tertiary carbon. And so this hydrogen that's attached will be called a tertiary hydrogen. These terms, primary, secondary, and tertiary, are terms that will apply not just to naming these hydrogens, but you'll see also this will be the same way we name carbocations. It'll be the same way we name radicals. It'll be the same way we name even halides. So this is a secondary halide, and that's a primary halide. So the key thing here is what non-hydrogen things, how many non-hydrogen things are attached to those carbons. Okay, so now let's look at this closely. First, we have to initiate, right? We still have to initiate. We can't get around that step. We have our molecular chlorine. We hit it with a photon. We get our 2 chlorine radicals. Then, in terms of propane, in our first propagation step, that chlorine radical can either take one of the hydrogen atoms from the end or one of the hydrogen atoms in the middle. So we're going to get either this blue intermediate or this pink intermediate, or a mixture of both. And then in the second propagation step, that blue intermediate will go on to abstract that chlorine atom at the site where the radical is. So it'll give you a 1-chloropropane. Or for that pink intermediate, if that's the one you have, that secondary radical will go on to abstract a chlorine to give you a secondary chloride. So what is the rate determining step here? And how do we know which of these things dictates what happens? Well, this step right here is where that branch point would happen. This is where that chlorine has to decide, do I grab this hydrogen atom or that hydrogen atom? And how do we know what happens? Well, turns out we can use the principles we just learned about. So we have a couple of different ways to think about this. The first way I want to think about it is using delta H. So let's go ahead and look at what the delta H difference is for these types of reactions. So we are going to be breaking a carbon-hydrogen bond in each case. In the top case, it's going to be a primary carbon-hydrogen bond. So we can look that up on our chart, see that it's plus 423 kilojoules per mole. And then we're going to be forming an HCl bond. And we can look that up at our chart and see that it's negative 432 kilojoules per mole, giving us an overall delta H for this step of the reaction of negative 9 kjoules per mole. For our secondary equation, this if it takes this hydrogen atom here, that bond has a different bond association energy because it's a different type of bond, right? They're both carbon-hydrogen bonds, but they're different because this one's a primary, this one's a secondary. So this bond association energy is actually plus 413 kilojoules per mole, right? It's a little bit easier of a bond to break. And so the overall delta H is a little bit more favorable, negative 19 kilojoules per mole. Notice that the HCl bond formation hasn't changed. That's the same in both reactions. So our delta H is a little bit more favorable in the secondary case, and that's what the driving force is here. That's one way to look at this, right? A more negative delta H is typically going to be more thermodynamically favorable, mostly because that delta S term doesn't really matter here, right? Okay, so there's other ways to think about this also. We can look for the lowest activation energy. We can also look for the more stable intermediate. So let's talk about that for a minute. These are the different possibilities for carbon-based radicals. The tertiary carbon-based radical is more stable. So the more substitution you have on a carbon-based radical, the more stable it's going to be. I'm probably not going to get to the slides that explain why this is, but I will on Wednesday. So for right now, just know the more substituted it is, the more stable it is. And so then if we think about in the reaction example that we were having, we were comparing this secondary radical with a primary radical. So the secondary radical would be more stable, and that would be the favored pathway. Okay. So we can also look at this visually on a reaction coordinate diagram, and that'll show us a number of different ways to think about this. So let's go ahead and look at it. Here's the reaction coordinate diagram for exactly what we were talking about. Here's propane, and the blue pathway leads to the primary radical, and the green pathway leads to the secondary radical. So you can see that the secondary radical is a little bit more stable than the primary. So there's a little bit of a difference. So that's one reason that this green pathway is favored. Another reason the green pathway is favored is that you can see from this reaction coordinate diagram that the activation energy to reach the transition state for making the secondary radical is smaller than the activation energy to reach the transition state for making the primary radical. So it's less of an uphill battle to go down the secondary pathway, right? So both of these things are valid reasons that say this secondary radical would be favored. Okay. Whew. The last thing I think I'm going to talk about today, maybe I'll get to a little bit more, but I want to go through what's called the Hammond postulate because it relates to another way of thinking about selectivity in reactions and what happens if you have different pathways that are competing. So the Hammond postulate is actually kind of intuitive when we get to look at it graphically. But before I show it to you graphically, I'm just going to read it to you in its, straightforward word version. And it's that related species that are similar in energy are also similar in structure. And what this means is that the structure of the transition state is going to look more like the structure of the closest stable species. So if the transition state is closer to the starting materials, it'll look more like the starting materials. If the transition state is closer to the products, it will look more like the products. Okay, what do I mean by that look like? So we've already talked a number of times about how transition states, or the mountaintops, have partially formed or partially broken bonds, but the intermediates, or the valleys, the low points, have fully formed or fully broken bonds. So in our favorite chlorination of methane example, we are going on this first propagation step. We're going to break the CH bond. We're going to make an HCl bond. The transition state is somewhere in between there, with the CH bond partially broken and this HCl bond partially formed. But whether this transition state looks more like a CH bond still intact or more like CH bond broken and HCl bond being formed depends on how close that transition state is to either the starting materials or the products. So for endothermic reactions, those transition states resemble the product. For exothermic reactions, those transition states resemble the reactant. For me personally, this is really hard to remember. These words and connecting these things are very hard to remember. I find it so much easier to remember when I see the picture. So I'm going to show you guys the picture. Here's the picture. On the left here, we have an endothermic reaction. Our products are higher in energy than our starting materials. And so our reaction coordinate pathway looks like this, where the transition state is closer to the product, right? It's endothermic, so we have a huge mountain to climb to then go downhill just a little bit. Because our transition state is closer in energy to the products, it's also going to be closer in structure. So our transition state looks more like an HBr bond formed and more like a CH bond being broken. And the flip side is true for exothermic reactions. In an exothermic reaction, remember, our products are going to be a lot lower in energy. The heats of their bonds are much more stable bonds, stronger bonds. And so we only have to go uphill a little bit to then slide down this big slope. So that means our reactants and our transition states are going to be closer in energy. And that means that our transition state is going to look more like the reactant. So you can see in this transition state, we've got a CH bond that is more formed and an HCl bond that is starting to form, but it's not really very well formed yet. Okay, so I want to show you an example of how we can put this into practice, how we can apply this, and that is in chlorination versus bromination. So let's take our propane, and instead of doing a chlorination of propane, where we're still having to choose a primary radical pathway or secondary radical pathway, what if it were a bromination? Well, if we do our delta H calculations using our table for bromination, we find out that bromination is actually an endothermic reaction. This is in contrast to chlorination, which is exothermic reaction. Bromination is an endothermic reaction. That means that the transition state for the bromination is going to reside closer to the products, or in this case, the intermediates of this step. That means that the stability difference between these intermediates, notice this is still just 10 kilojoules per mole difference, because they're the same radical intermediates here, right? So the energy gap here is the same, but because our transition state is closer to the products, the activation energy gap is going to be bigger for this bromination case. And what that means, this is really cool, guys, really cool. That means that if we want to do a bromination, instead of just favoring our secondary product by 60%, the way we do in chlorination, now we've got 97% favoring that secondary pathway. And that difference, that shift, is because this activation energy gap is bigger for the bromine. So the lower energy pathway will be even more favored than in the case of chlorination. So in chlorination, the secondary radical pathway, the lower energy pathway, is favored, but it's favored even more in bromination because that energy gap is different and is bigger. Pretty cool, huh? Okay, so we just finished up Hammond postulate. I will save reactive intermediates and talk about them on Wednesday. Reactive intermediates will not be on the quiz. Everything else is fair game for the quiz, okay? All right, any questions? All right, guys, thank you. I will post these slides as soon as I can so that you guys can enjoy them for your studying pleasure.
I got, one question for you, not quite related to this.
That's fine. Go ahead.
So I know you said you didn't want to really record videos. Is it possible, like instead of like going through anything SEO-wise or anything, I have really bad ADHD, so I can pay attention a decent amount, but today was a definite lecture. To remember all that for me is incredibly hard. And then going back and then reading a book can get me so far, but a lot of things that you say and the way you teach it, like for like an old example is the things part of it, it makes it a lot easier. Is that something you'd be willing to consider, or would you like me, I guess in that case, to go ask them first and then contact you or anything like that?
Yeah, so my overarching goal is to make sure that everybody is as engaged as they can be. And when I record and when I post recordings, I lose engagement for a lot of the class. I've tried this in the past and that's been my experience. So I hear what you're saying and I appreciate your feedback. But the best way to do this is to talk to me offline and let's try to figure something else out. Okay?
Okay.
Okay.
All right. Thank you.
Yeah, you're welcome. Thank you.